in Philadelphia. And here's a picture of, where's my, here we are, Broad Street Station. Broad Street Station was built originally in 1881, and that portion of it is over here. And within a few years, in, let's see, 1892, they had to already expand the station. And in fact, it just couldn't handle the number of trains coming in. And so this portion of the, station was built. This is a Frank Furness, the architect, a real gem of a building here, long since gone, of course. But anyhow, the station was expanded, and by 1910, there are 578 arrivals and departures per day. And when you think about it, that's a lot of trains coming in and out of the station. And when you see the other side of the station, you can see in part what the problem was. It was a stub-ended station. And so all the trains, this is steam era, are coming in, the locomotives are coming in, but then once the passengers get off the train, you've got this business of turning the whole train around. And in a stub-ended station, that's a big deal. And, you know, you have to pull the train out, turn the locomotive, et cetera, et cetera. So, and if you're dealing with 500 some trains a day, that's a lot of traffic going on there. And so it was a real problem. And for a while, the PRR actually thought about even expanding it further. The fact is that that area, I mean, it's Center City, you're right across the street almost from City Hall. There's no place to build anything. And so the PRR then decided, well, maybe we should try something different. And I should say that part of this issue of the traffic and the huge number of trains per day was the fact that the PRR had been building any number of little branch lines from Center City out to the outskirts of Philadelphia. So there was trains out to Paoli, Westchester, Chestnut Hill, and so forth. Now, when you think about it, that's all commuter traffic, really. People coming into the city and then going out at the end of the day. And so that 578 trains is not an even distribution over a 24-hour period. It peaks in the morning and then late afternoon. So it was a significant problem. So what the PRR decided to do was to electrify from, I don't know if you can see my cursor here, from Broad Street Station out to Paoli. Okay? And the idea was that let's try and electrify this route, and at the same time, they took 93 P54 coaches and converted them to MP54s, which means they were motorized, and these were electric motors, and you can see on this picture here the pantograph line down here. And we would electrify and run basically these as commuter trains. And people probably don't realize, but at the time, this was just a significant event. And when they ran the first train from Paoli in 1915, I mean, they did practice runs and so forth, but the first one where they actually had people on board, crowds lined the tracks from Paoli down into the city to see these MP54s going by. And it was just a tremendous success. because all of a sudden you, first of all, had a shorter time that for the route from the Broad Street Station to Paoli than you did with a steam locomotive. Second thing is, you didn't have the problem at Broad Street Station where you had to turn the engine. You simply had the motorman walk to the other end of the car or cars, and you could just then pull the train out that way. And also the absence of a tremendous amount of smoke from the steam engines would be gone. And so I have to say it was one of the PRR's really big successes. And so this happened in 1915, and you know, the PRR, like, wow, okay, we got to do this. So they decided to electrify the Chestnut Hill Branch, and they started planning this in 1915. And there was a lot of work in terms of getting rid of grade crossings, and Gibson Hill were the engineering company. They consulted them on it, and so by 1918, and you can see this over on the right side here, the line was essentially electrified, effective March 30th, 1918. And they note that, in fact, it's probably not wise for employees to go up on top of boxcars with the electrified line just above them. So the interesting thing is that the original electrification to Paoli, and I'm trying to find my cursor here. Okay, they come out of Broad Street Station over West Philadelphia, and they head up here, and they're going to go out basically the main line to Paoli. And that time this was referred to as Mantua Junction. And so for the Chestnut Hill line to be electrified, it wouldn't be any good unless you also extended the electrification from Mantua Junction up to essentially where the Chestnut Hill Branch comes off in North Philadelphia. And so this 3.1 miles had to be electrified along with the electrification of the Chestnut Hill Branch. Okay, so prototypic modeling of PRR electrification has two components. One, it's the wire components, the catenary itself, the messenger, auxiliary, and trolley wires. And all of that has to be put into on some sort of supporting structure, poles and bridges and so forth. And so for modeling purposes, Andy Rubo, back in 2007, published a series of articles in TKM. And you can see the titles here. The first one was on the K Bridge, which holds up the catenary. Then part two was the wire structure itself. And part three was catenary on curves. All of these actually, if you're interested, and you haven't saved your Keystone modelers, you can get it on a CD from Jim Hunter, who's the editor of Keystone Modeler. Now, the interesting thing is, this is what's called the K Bridge, which is what Andy started out with, and this is a picture from his phenomenal layout of all the catenary strung and being held up here by what was called the K Bridge. And actually, when you look at electrified territory, the PRR, probably 90% of the catenary structure, the supporting bridge structure, are K bridges. And but initially, on the way to Paoli, they did not use K bridges. What they used were telescoping tubular poles like this, and this is a blueprint of one of them. And so the line to Paoli has this sort of structure. And also, it turns out the Chestnut Hill Branch, which was done immediately after the Paoli line, has this kind of catenary support. And these can actually be relatively easily modeled by a series of brass tubes that you then put together in this sort of telescoping tubular or structure. And so this is a model of this kind of catenary structure. This is on my layout, which is part of it is the Chestnut Hill Branch, and this is kind of what it looked like, right? So, what was that? Okay, so what I then began looking at, because part of my layout covers this territory, are the catenary bridges between Mantua Junction and North Philadelphia Station. And I don't know whether it's fortunate or misfortunate, but it turns out that this 3.1 mile stretch has the most unique catenary bridges on the PRR. You don't find them anywhere else. And this was, again, very early work, because remember, these have to be placed in service in 1918 to connect up the Chestnut Hill Branch. So this is a nice picture of one of these structures. Here's another one. This is down by 22nd Street, and it's very unique structure. You just don't find it anywhere else on the PRR. So there's a number of these. I haven't counted them up, but they're along that 3 mile stretch from basically what we call now Zoo up to North Philadelphia. So what are the challenges for modeling catenary bridges? Well, first of all, you want the bridges to be sturdy and ideally of brass, because once you put in the effort to put the catenary onto this, you just don't want somebody to come and nudge your bridge and bring down a year's worth of work in an instant. So I like, both Andy and I like to have something that we feel is really robust and might withstand a nudge from an errant hand or arm. But there are some difficulties that have come up over that time period. So when Andy wrote those articles in TKM in 2007, a company called Special Shapes was still in business, and they made just all sorts of brass shapes, H-beams, I-beams, in all different sizes and so forth. The problem is that a few years ago, Special Shapes went out of business, and so getting a lot of these things is very difficult now. K&S, which is the parent company for Special Shapes, still carries a limited selection of brass, and I've used some of that, but it's definitely much more challenging now than it was, say, 10 years ago, doing some of these structures. The other thing that's come up is that there are limited options for brass shapes from a company called Albion. They are in England. They don't import directly to the States. What you have to do is go through a sort of intermediate person who's in Canada, and you can order. They have a number of useful brass shapes, but it's very expensive, and you can't get them in the lengths that you used to be able to get special shape. So it is challenging, even more challenging now doing this kind of thing. So what Andy and I have decided to do is try what we call a hybrid approach. And so the first thing is to try and build some underlying structure with brass components. So, you know, your structure will be robust. And then what may have been used in the past, where you did with lots of little brass parts, you now substitute styrene components. And this seems to have worked fairly well. And I'm going to show you some of the things that have been done. So I'm first going to start out talking about the catenary bridges that I showed you in that the two pictures. And what I've done is we have K&S. This is well, a 64th by 1/4 inch brass stock, and we have the two legs with that. And then we have the Albion angle stock going across the bridge. And for those who are sort of catenary aficionados, this is also the steady span you can put in at this time. This is phosphor bronze wire, and also the hangers for the messenger wire. Now, you'll notice that the legs are not even. And that is the track level for this catenary structure is going to be right along here. And what we have is we have one leg extended several inches below that. And the reason for doing that is that I've used what I think is one of Andy's brilliant ideas, is to put outriggers below your bench work so that you can slide this leg into the outrigger, and the outrigger then has screws, a screw that's perpendicular to the leg, and as you lower this in, you can tighten this screw and it holds the bridge in position. Now you say, well, why do you want to do that? Well, in the end, when you're doing all this catenary stuff, there has to be a fairly great deal of precision here. This point right here has to be 22 scale feet above the railhead. And if you're just putting on some sort of structure onto the layout, you're going to have a challenging time making sure that you're exactly at the right height. But with this outrigger, you're allowed to slide this thing up and down until you get it in just the right position, and then you tighten the screws. And later on in the talk, I'll show you one of these outriggers. Okay, so once we have the brass portion done, then we can add the styrene portions that are make up a lot of the detail. So the first thing is on the legs. You recall they were all lattice, and this is Central Valley lattice that you can just. It comes actually as a L-shaped thing with solid plastic. You can just cut that off. And so you have lattice on each leg. You also, and I don't have a top-down view, but you recall in that picture I showed you, there's lattice also across the top and the bottom of the bridge itself. And then you have vertical components here, which is again styrene holding this up, and then there are turnbuckles that go crosswise for each of these intervals like this. And then there was a special part here that has sort of oval cutouts, and that I do on a digital cutter and just cut those pieces and put them in. And at the bottom, most of these, certainly these lattice type poles, were not just plunked into concrete, but they actually had a steel sort of sleeve that it sat in. And so I have some picture. Didn't bring the pictures along for this, but close-ups from I took down in Marcus Hook, where you can see what the structure is for holding these lattice poles in the concrete base. Okay, so the other feature you notice so we've covered the lattice poles here and all the stuff going across here, the turnbuckles and so forth. Now we're left with the transmission poles, and these were very important because we needed, these lines here for the power. And you'll notice that the poles are not simply straight lattice like here, but they're, excuse me, pyramidal. One over here and one over here, and also the varying height, and you can see what that looks like. And also this is a nice prototype shot of here's your steady span going across here on the hangers for your messenger wire. And here's another, excuse me, example up in North Philadelphia, where you have your pyramidal poles. And the important thing I want to show here is that the location of the pole can change, meaning here they're on the outside. Okay, and if you look at, for instance, remember the picture I showed of Andy's Cape Bridge, the transmission poles are on the outside. But in North Philadelphia, you have a problem, and that is this stretch of trackage went through a canyon of factories. So on this side, you can see the buildings here. This is obviously a very recent shot, but when the catenary was first put in 1915 to 18, there was actually a sister building to this that ran along here. And so what the railroad did then was to move those transmission poles inward so that they did not have interference or be too close to the buildings. Okay, so how do you make the pyramidal poles? Well, what I did was made a jig, and this has blue painter's tape sticky side up. And then what I put in there are two evergreen styrene I-beams that I, put on the tape so they sit nicely there. And then what I've done on the digital cutter is to cut the chevrons. And the reason I want to do the chevrons is because when you take, for instance, this fella and flip it over and put it on top of this one, you get your lattice, okay? But the other nice thing is it's dimensional, meaning a lot of manufactured lattice, not the Central Valley, which is very good, but a lot of the other stuff, it's in a sense two-dimensional. There's no over and under of the straps because that's technically hard to do when you're just molding something. So anyhow, what you do is you, and this was all designed so that, it comes down with the proper, spacing for these lattices. And so you put one chevron over the other, and then you carefully sequentially glue this down the length of your pole. And then you can take that and off the tape, turn it over, and do the same thing on the other side, and you have your pole. And so here on the layout, you can see I have one pole here, one here. And what I decided to do was, even though technically in the prototype there were buildings here, on my layout, I moved Margie Yard up, so there is no building here. So I thought it's better to at least follow the prototype, and if there's no building in the way, put the pole at the edge. On the other side, you see where I have all these buildings, I've moved the transmission poles inward to kind of reflect that notion. Okay, so what I've shown you are the most frequent of the bridges going up this 3-mile stretch from Zoo. But there's a very interesting photograph that has appeared on the internet, and this is obviously some time ago. And the location of this is North Philadelphia. Over here is C.H. Wheeler, and in back here is the building actually that I showed you on a prior slide. And if you look carefully, here is the Margie Street Bridge with Margie Yard back here. And here's the GG1. And what's really interesting is if you look at this catenary bridge here, it looks cantilevered. And when I first came across this, and I asked some people, I said, gee, was there really a cantilever bridge there? And most people thought, no, there's no way you could do a cantilever catenary bridge of this size, across basically 6 tracks. Well, turns out this is from the Hagley Digital Archives. These are Dahlin aerial photographs, and here's Shive Park at the time, later Pontiac Stadium. And if you look up in this right-hand corner here, this is the location for that catenary bridge. And if you zoom in on this, it turns out there you can see it. And it is indeed a cantilevered bridge over basically 6 tracks. And that was really something. So the question is, why did the railroad do that? I mean, it sounds kind of extraordinary. Well, and here's another picture, actually. This is taken in the early 60s. This is from phillyhistory.org. And there you can see that cantilevered bridge right there. Here's Lehigh Avenue, and it's just north of that. So why did the railroad do it? Well, it turns out, if you go back to the sandboard maps from this time period, which is about 1915, what you see is, in fact, that bridge is right about here where this red arrow is, and it goes across these tracks. But then there are 2 tracks that go into C.H. Wheeler. And when you think about it, there's no place for a vertical support on that side for the catenary bridge. So they made it cantilevered. Now, as it turns out, well, let me finish the story. So they built this cantilevered bridge. It lasted until about 1980. I've looked at aerial photographs. And then sometime around 1980, there was either a derailment or a fire or whatever, and Amtrak decided to replace it. And so here is that location, and this is the Amtrak replacement bridge. But you see now they could put vertical supports over here that they couldn't before, because here are where the 2 tracks used to enter C.H. Wheeler. So that's what happened. Okay, So I wanted to put this on the layout. And so the first thing I did was I made just a totally styrene mock-up to see how it might look. And the location, because I wanted to put it, and this is what was called the Frishman building, and it's still there. And the Mantua Branch was right there. So I wanted to see how it looks. And so it seemed to be okay. And I had actually kind of a good excuse on my layout because here's the lead from Margie Yard going here, and I really wouldn't have space to put another pole to support the catenary across here. So it's serving much the same function as the prototype. So Andy and I got pretty excited about this project, and so the first thing we did was to make a scale drawing, because we had no blueprints available, and decide how to make this bridge. And I have to say, it's one thing to make that structure out of styrene, it's another to do it out of brass. And so when Andy volunteered to say, well, I'll do the brass structure, it was like, oh wow, I can't believe this. And he did. And we're going to see how we put this together, because believe me, this is not a trivial piece of work. Okay, so Andy's strategy was first, let's do the vertical supports, which we're here, over here, okay, where the heavy black line, and connect these up. And this shows how he's got it all clamped to the table, and then soldering the brass here at 10-foot intervals. And when Andy says scale 10 feet, he means 10 scale. It's not 11, not 9.5, it's 10. And so here, what he's done is the one side of the vertical support, and now he's put on what are going to be the bridge itself. Okay. So here's our drawing, and here's what he's soldered together so far. So first of all, you notice that the legs are extended below because they're going to go into an outrigger. The other thing you'll notice is that, in fact, this top board is now bent so that it goes much like the prototype, goes down over here. And to do that, what Andy did was he sort of nicked the brass here with a fine cutoff disc, so that it gives it a little flexibility so you can bend this down here in this smooth bend. And we kind of decided the end should be about 3.5 scale feet apart. All right. Okay, so now this becomes a very interesting sort of topological issue. Okay, if you've made this, okay, and you've actually made two of them, and then how to assemble this into the three-dimensional structure in the end. And so if you look very carefully, here's the top border going down off the bench, and he's got this clamp down, and he's now assembling the two halves of the catenary bridge. And so the top view, and here's another important issue, and that is that when we looked at these pictures, albeit, it was from a distance, you could tell that the bridge itself also is, not only is it going downward, but when you look on the top view, they're also coming inward like this. So this distance is also 3.5 scale feet. And so again, what Andy did was he put some nicks in here on these so that you can bend these. If you just try and bend it without those, doesn't work. So he's bent these, and to do this, he carefully made a template. Okay, so here's what would be the center of the structure and the center line, and he's got to, come down to 3.5 scale feet here from 10 scale feet here. And there it is. And so he can put this in here and then basically solder the two top boards together with solid brass. And if people want to look at a detailed description of this, it's in the latest issue of the Keystone Modeler. And so this is what the brass structure looks like at the end. Yes. Yes. Okay, so now once this is in place, I get the job of putting on all the detail. And so this is the detail. And again, we carefully look at the pictures, that particularly that one that's online with the GG1 underneath. And so, for instance, all of the vertical supports you can see from the pictures had sway bars to stabilize the structure going across here. And so there's sway bars, gusset plates to hold them. And then for the prototype, the sway bars are actually, you have one solid one going across, and then the one underneath is actually separated, okay, but then held in place by a gusset plate that holds the whole thing together and also attaches it to this sway bar, right? So we go around the structure like that. We also have the same thing up on the top, connecting the two top cords. Also, the two bottom cords are connected that way. And then there were turnbuckles, which seems to be a very characteristic feature of these catenary bridges in this 3-mile stretch. Although, as opposed to the ones that I showed you earlier, the turnbuckles were only in one direction like this rather than making crosswalks there. Okay, so then, so this is the structure all detailed and painted, and then it was time for putting in the transmission poles, okay? And for this, we, I'm not sure I can pull up exactly what evergreen styrene was used here, but it was basically like a very small H column for these. And then this is angle stock for plastrut that forms these cross braces and put the hangers down. Okay. So there you have the structure that's been painted. And now we put it onto the layout. And so this is a picture of the turnbuckle underneath. So here's the sub roadbed. It was fastened with this block. And here you see the 4 legs coming through this block. And here are the thumb screws to tighten each leg then as it comes through, so you can adjust the height of the bridge. And, so here's the final installation. Looks a lot better than that styrene thing. And Here's some catenary strung underneath. And here's a view looking down. Here would be where Margie Yard comes out. I won't talk about it today, but there's a signal bridge back here. And then beyond that, there's a few months of catenary work to be done to hang the rest of the catenary. And so then we get to the final sort of point. So why did this section from Mantua Junction to North Philadelphia have such unique catenary bridges? Because you don't find these anywhere else in the PRR. And why not the standard K bridge? And I think the answer is, in a sense, technology. The K bridge uses H beams. Well, it turns out H beams were, well, the Bethlehem Steel got a patent for them in 1908. In 1911, they started appearing in the Bethlehem Steel catalog. But I think this was very early on, and I'm not sure that, for instance, the K bridge that I showed you earlier from Andy's layout, we're talking about a beam that's got to be about 100 feet in length. And I think this was a technology that was being developed in this time period, but I suspect it was not really available. So that the PRR chose this alternative way of doing it with the lattice structures that I showed you in this time period. And it's kind of interesting when you look at then later electrification. In 1924, I don't have it on here, but the Fort Washington branch was added onto the Chestnut Hill branch. And they used actually cedar poles, basically telephone poles, for the electrification. And it's not until 1926 that you start seeing K bridges, which appeared on the Westchester. So I think what this probably reflects is that H-beams were not really widely used at this time period, or were being sort of developed, and the PRR went with the alternative. And finally, here's an old PRR holiday greetings to everyone, and hope everyone has a nice holiday and Happy New Year. And that sort of concludes my presentation. And I'll take any questions.
Anybody online have a question? Feel free to unmute. We have one chat here. Michael Davis, great history, amazing work. Great.
Okay. Any other questions?
This definition for K bridges, K components.
Well, I think the easiest thing, let me go back to Andy's picture here a minute. We'll get there. Okay. Sorry.
Looks like slide 11.
Yeah, this is slide.
Right.
See if I can do this correctly.
Okay.
There we go. Okay, so the K bridge, basically, you have these two H columns here, and then there's another piece that goes across here, but this is supported then by this, if you turn it on its side, a K-like structure. So it just gives this cross piece much more stability. Pardon?
K is more structured than if the 2 point connected with the.
Yeah, I think so.
The online question in this beginning, what was used for insulators?
Model or real? Model, I assume, tissue insulators. And Don's Don Tissue's insulators are really very nice. I mean, they're basically prototype. And what you can do is you can buy them by the big box full, because the transmission pulse, each of these are a string of 11 insulators. And so you can go through quite a few.
Rob, what kind of glue do you use, like when you're attaching all of the styrene plastic to the brass?
I've been using CA.
That holds up well for you?
Pardon?
That holds up well for you? The
Yeah, yeah.
I can make those concrete bases.
Those are basically, you know, styrene, but then on some of mine, what I've done is just made a mold, and then I resin cast them and then take them out.
Was that Pennsy standard practice to paint all the catenary poles that silver shade?
Yeah, that's actually a good question, and they vary. I mean, if you look at the current structures, they're black or rust, okay? And I think they started out maybe black, but then I came across at least one reference where it said then a final coat of this sort of aluminum shade of paint. And if you look, what I tried to do was look back at pictures of the time period that I'm modeling, which is like 1958. And it certainly looks like most of them were sort of this aluminum type color. But yeah, if you went down there now and you look at the current pictures from Jim, none of them are that color. They're basically black or rust, mostly rust.